In this video, I'm going to do a summary of the scope test. It's called that, but it's really just a very simple oscilloscope. At the moment, there's no real triggering or anything, but it lets you see waveforms and it's easy to see things like distortion. So let me start. We support two generators. I'm currently running with one. If I click start, it'll just run this once. So we have a 1 kilohertz sine wave at 1/10 of a volt, RMS. And here's the waveform. If we want to zoom it up, we can do that. If we want to look at it in gory detail, we can do a zoom here. But fundamentally, this is exactly what you'd expect a sine wave at 1 kilohertz. Unless there are things wrong. Now, for example, if I switch this to like a square wave and I run this, we're going to see something very different. It's not actually going to be a square wave. It's a square wave showing ringing, which is not surprising because we have a very steep filter on the output of the generator and the input to the sensing to avoid getting noise issues. So what we're seeing here is exactly what an oscilloscope would see if we hooked it up to the output of the device under test. All right, and in order to test all sorts of things, we have a bunch of waveforms we can support, and we can support two of them at the same time. So if I want to, I can run a 1200 hertz at 2/10 of a volt, and let's go ahead and just run this free running. And it looks like that. Now, something to think about is when you have two oscillators, it's kind of nice to keep the auto ranging on because you never really know what the total voltage will be when they're essentially added together. And a good example of that is multitone. So if I run multitone at 1/10 of a volt and leave it on auto range and I click start, watch what happens. It auto ranges at 12 dB and the voltage levels are high. And that's because if I go back to spectrum for a second and I set this to multitone, you'll see what the multitone actually looks like. It is a bunch of sine waves, if you will, or a bunch of frequencies all at 1/10 of a volt. And when you add them all up, they're a bunch. So having auto ranging on is a good idea, at least at first. All right. Okay, in addition to sine waves and square waves and impulses and a chirp, here let's take a look at the chirp for a second. Well, at the beginning of the chirp, it's very low frequency. Let's zoom out a little bit, and that's what a chirp looks like. Low frequencies and then high frequencies. Now, in addition to all of those, we can use as a waveform any wave file. And when we do that, this changes to, instead of letting us determine the frequency, we determine the actual file. Click here to get a selector to determine what you want to actually look at. And I've got something strange in here called cantina band. And the 1/10 of a volt will be used to scale the wave file. But if I run this wave file once, what we're going to see here is nothing. And that's because this starts off with a bunch of silence. Let's go ahead and fit to data. We'll see all of the data in the packet. And here's the cantina band. And the way this works is we resample the wave file to fit our 96 kilohertz, and then we truncate it to fit. So if I increase this from 64K to like half a megabyte at 96 kilohertz, this is 5 seconds. And now if I start, we'll get 5 seconds of the cantina band sound. And yeah, it's going to take 5 seconds to acquire the data, and it's done. And now when I fit to data, we have 5,000 milliseconds, and here is the entire wave chunk, and then silence when it finishes. And if we were to actually play this result, it would Sound like the Cantina band wave file. All right, so other than that, there are a couple of things you can do. You can bring up summary data, which is pretty limited and mainly shows peak to peak and RMS voltages. And of course, you can change the test info, but you can also bring up the residual plot. And let me switch from wave file back to sine for a second. Let's make this a sine wave at a volt, which is going to generate a fair amount of harmonic distortion on the device I'm actually testing. And let's go ahead and run this once. All right, so now we're going to get a 1 volt sine wave. Oh, let me cut this back from half a meg to 64K so it runs quickly. There we go. Now let's look at the first 10 milliseconds of this, or so, okay? Here's my sine wave, and I've told you there's going to be some distortion, and how can we see that here? Well, if we turn on a residual plot, what it will do is it will show us the signal minus the fundamental, just the distortion components. And that's shown over here. I can zoom in and out, and it's called the Y2 axis, so I can do things like pin the current settings. But this lets you see exactly what's happening sort of under the hood. All right, one last thing is just to note, this is really kind of interesting. If I run this single sine wave at a kilohertz, let me go ahead and do start. Let's go ahead and run that just one time. And now I'm going to fit it to data. And at a volt, this isn't so obvious. Let's cut this down to 1/10 of a volt. There we go. At a lower voltage, we see this. Now you'll notice something strange when I fit it all to data, and that is there's this little triangular gray area up here, and the same inverse area down here. What's happening is that the analyzer itself is settling slightly over time. In this case, it's about a second. And after about a second, it has drifted. It's a slight DC change as it gets settled. And just note that that'll be here. So if I look at the first like 10 milliseconds of this, there's white space at the bottom. And if I look at the last 10 milliseconds, which is kind of hard to do here, you're going to have white space at the top. And if I run this continuously, so let's go ahead and fit it to data again. Watch what happens. What you see is that after it runs a couple times, it's now flat because the instrument is settled out. So just to know, there are some startup time issues, but usually you don't care. As you could tell, this delta is pretty small. All right, still, it's kind of nice having an oscilloscope, and that's what this is.